Hello everyone, welcome back to Math with Allison. Today we're working in our curve series, so we're going to be talking about roses. They are a form of polar curves. So let's go ahead and dive in. Here we have a little summary of the polar curves I have already looked at if you're interested in looking at those videos. First we have a circle, right? We have a circle centered at the origin, right? That's going to be r is equal to some value a. And then we have two other forms. So r is equal to 2a sine theta and r is equal to 2a cosine theta. And so those two are going to be circled center at the point. This is going to be 0a, and this one's going to be a 0, right? So either we extend up into the y-axis or we extend over into the x-axis. We have lines, and that's going to be of the form that theta is equal to some value a. Spirals is going to be r is equal to a times theta. We have cardioids, right? So that's going to be r is equal to a plus or minus a sine theta or cosine of theta, right? And cardioids are actually a very specific case of lemmasons. So here we have lemmasons are a plus or minus b sine theta. So that's when a and b are different, right? And there are different cases for when a is greater than b, a is less than b, and all those different things. So the next type of curve that we're going to move into today is called a rose, and it has two forms, right? So we have r is equal to a times sine of b theta, and r is equal to a times cosine of b theta. Notice this is super similar to our circles. We have 2a sine theta and 2a cosine theta. The only difference here is we have b times theta. So on the inside of the sine or cosine, we have a value times our theta. Here's a beautiful image from Wikipedia. It's literally the Wikipedia page for roses. And we have some drawings of what these are going to look like. So let's go ahead and dive in with an example. Here we have r is equal to 3 times sine of 2 theta. So we're just going to go ahead and plug and chug. We want to evaluate this curve at different theta values so we know how to plot the radius. So let's go ahead and do that. First, we are always going to start out, right, with a theta value of 0. So let's go ahead and plug that in. We get 3 sine of 2 times 0, which is just 0. And we know 3 sine of theta is indeed equal to 0. So here, let's go ahead and plot that point. We are starting at the origin. Now let's go ahead and go up to pi over 6. Here we get 3 sine of 2 times pi over 6, and that simplifies to pi over 3. I never have these memorized. So what I always do is I draw my triangle. I know I'm in the first quadrant, so my triangle will look like that. I know my hypotenuse is 2, and my angle is pi over 3. Pi over 3 is the bigger angle, so this is 60. This one is 30. And I know the two legs are the square root of 3 and 1. The bigger leg goes diagonal from the bigger angle. So this is the square root of 3, and this one is 1. The smaller angle is diagonal from the smaller leg. So here, sine is going to be opposite over hypotenuse. So I get 3 times the square root of 3 divided by 2, which we are going to use our handy dandy calculator in order to calculate that. So 3 times square root of 3 divided by 2. We end up with I'm going to round up to 6, 2.6. So let's go ahead and do that. We're going to go to our angle, pi over 6, and we're going to go out a radius of 2.6, which is going to be a little more than halfway, so right about there. Now let's go ahead and keep filling these in. So we're going to just move on to our next angle, which is pi over 4. So here we get 3 sine of, now pi over 4 times 2 is equal to pi over 2. We know that sine of pi over 2 is equal to 1. So here we get 3. So we're going to go ahead and go to our angle, pi over 4. I'm going to extend a radius of 3, which goes all the way out here. Now we're going to go ahead and do the same thing with pi over 3. So here we get 3 times sine, and that's going to be 2 pi over 3. And let's see, sine of 2 pi over 3, so that's going to be super similar to our other triangle. The only difference is that leg is now going to be in the other quadrant, so I'll go ahead and draw that actually. We go out this way now, so this is going to be -1, square root of 3, and 2. But that does not change our sign at all, right? Because sine is opposite over hypotenuse. So again, we get 3 times the square root of 3 divided by 2, which we already calculated to be 2.6. So here we're going to find our angle, pi over 3, and we're going to go out a distance of 2.6 again. So again, probably right there. And what we just did was we plotted our first petal. So from the origin, we're going to go around like this, and that is our petal. That is not our only petal. Notice that our petal extends to its fullest length at pi over 4. So if I want to see where all of the petals are extending, let's go ahead and look at the other pi over 4s, right? So first we're going to go ahead and plug in, that's going to be 3 pi over 4 in the second quadrant. So we get 3 sine of, that's going to be 3 pi over 2, because we have to multiply it by 2, which is equal to negative 3. So that's interesting. When we go to 3 pi over 4, we're going to extend backwards in the opposite direction. So we're going to extend in the 7 pi over 4 direction, a radius of 3. So that's going to be another one of our petals, right? If we were to plug in these other theta values right here and here, we would also get about 2.6, right? So let's go ahead and draw out our next petal. And now let's go ahead and plug in where we need to test out 5 pi over 4. So here we're going to plug in 5 pi over 4, right? When we do that, we end up with, instead of 3 pi over 2, we end up with 5 pi over 2. So what is 5 pi over 2, right? That's going to be 2 pi plus pi over 2. So what we're going to do is we're going to treat it as pi over 2. And we know sine of pi over 2 is equal to 1. So 3 times 1 is equal to 3. And we're going to go ahead and extend out that radius of 3. If we plugged in these other theta values, right, we would get 2.6. And here we would get another one of our petals. You can probably guess where the last petal is going to go, but of course we're going to plug it in. 7 pi over 4. When we plug that in, right, we end up with 7 pi over 2, and that is equal to 2 pi plus 3 pi over 2. So again, we're going to pretend, so we can pretend that we're evaluating this as 3 sine of 3 pi over 2, because we know sine of 3 pi over 2 is negative 1. So again, we're going to have that negative radius, which means we're going to extend in the opposite direction. So we're going to go out 3 pi over 4, a radius of 3. Here we would get, these would be negative 2.6, negative 2.6. And here we would have the last one of our petals. So if you recognize the function here, we have r is equal to 3 times sine of 2 theta. We would see that this is a rose. Now, if we know it's a rose, what you can do is you can just draw out one of the petals and you can repeat it in the following quadrants. Just to test that this is true, let's go ahead and plug in some other values. So another value that we could plug in that we didn't, right, was this one right here, which is 2 pi over 3. Let's go ahead and see what happens when we plug in 2 pi over 3. We end up with 3 sine, and that's going to be now 4 pi over 3 because we multiply it by 2. So 4 pi over 3, that is going to be in this quadrant, right? This is our 60, which means this is our root 3, but we're going down, so it's negative. This is our negative 1, this is our 2. So here we get 3 times negative root 3 over 2. That is going to be negative 2.6. So in that 2 pi over 3, that is where we shoot backwards into this direction right here, and we go out a distance of 2.6. So if you wanted to plug in more theta values to plot it out, you totally could. You don't even need to stick to the main theta values. You could also plug in ones that you want. So an example of that would be pi over 12. If we were to plug in pi over 12, that would be like this little angle right here, right? We're halfway to pi over 6. So if we wanted to plot that, we would just plug it in. We'd get 3 sine of 2 times pi over 12. That's equal to pi over 6, right? So, see, I literally don't have it memorized. So pi over 6, that's a smaller angle, that's theta. So this, or 30. So the opposite leg is 1. This is square root of 3. This is 2. So sine of that is going to be 1/2. So we get 3 times 1/2, which is equal to 1.5, right? So at pi over 12, we would go out a distance of 1.5, which we can see with that point right there. So you can also plug in values that aren't necessarily the general ones we use. So let's go ahead and talk about the number of petals that we have. Notice that we have 4 petals, and within our sine, we have 2 theta. So we have double 2, right? We have 4 petals, but we have 2 theta. Think about that. I'm going to let that rest in your mind. And now we're going to go to r equals 2 cosine of 3 theta. Do you think we will have 6 petals, or do you think we will have 3 petals? Think about it. Okay, let's go ahead and try plugging in some values. We are going to start with our favorite, 0. So here we get 2 cosine of 0 is equal to 2. So we're going to extend all the way out a radius of 2 when our theta is equal to 0. Now let's go ahead and plug in pi over 6. So here we get 2 cosine. That's going to be 3 pi over 6, right? Because we have to multiply by 3. So 2 cosine, and that's just pi over 2. This is equal to 0. So here we go back to the origin. Now this isn't very interesting, right? I go all the way out a distance of 2 and then I'm back to the origin. So maybe we should see what's happening halfway between pi over 6 and 0, which is going to be our pi over 12, right? I want to know what's happening between there. So here, let's go ahead and plug it in. We get 2 cosine. That's going to be 3 pi over 12 when I multiply it by 3, which is 2 cosine. That's going to be pi over 4. We know this is equal to root 2 over 2. And those 2's cancel out, so we're just left with the square root of 2, which I think is what, 1.7? Another thing I don't have memorized. Some people memorize these things. It's impressive. 1.4. So notice there is something happening right there. So at pi over 12, we go, which is, going to be halfway to pi over 6. We're going to go a distance of 1.4. So something like that. Yeah, pretty good. Now let's see what's happening below that, because it almost looks like here we have half of a petal. So maybe we should go to negative pi over 12, right? So here when we do that, we end up with 2 cosine, and that's going to be negative pi over 4, right? When we multiply by 3, that's going to simplify it like that. So here, negative pi over 4, and again, I'm going to draw my triangle this time. We're going down in this direction. This is 2. This is the square root of 2, square root of 2, but downwards we're going negative. So here, this doesn't change the radius at all because cosine is opposite over hypotenuse. So here we get 2 times the square root of 2 over 2, or just the square root of 2. So we already found this to be 1.4. So here when we go out our angle of negative pi over 4, which is going to be right there, we're going to go out a distance of 1.4, which is going to be right about there. And here we can see our first little petal. So our petal is going to go around like this. Okay, so we have the first petal and we stopped at pi over 6. So let's go ahead and go now to pi over 4 and see what happens. We get 2 cosine of 3 pi over 4. That is equal to, so that's in this quadrant, 3 pi over 4. So negative root 2, 2. Cosine is adjacent. We're going to go 2 times negative root 2 over 2, right? So that's going to be negative root 2. So at pi over 4, we need to go backwards. This is going to be a radius of negative 1.4. So if we go backwards, we're actually going to extend in the 5 pi over 4 direction, right? So that's going to go out a distance of 1.4, which is going to be right about there. Maybe we should see what happens at pi over 3. So here, let's go ahead and plug in pi over 3. 2 cosine of 3 pi over 3. Those 3's are going to cancel. We're left with pi. Ooh, we get negative 2. So that's going to be the whole length of our petal, right? So we're going to go out in the opposite direction, and we're going to go out a radius of negative 2. And now I can kind of see already my petal. If I were to plug in this value right here, right, that's going to be halfway between pi and, is this 7 pi over 6? Yep, I think it is. We're going to be halfway between pi and 7 pi over 6. And so here we can graph our next petal. We go from the origin all the way around. So we went all the way to pi over 3. Let's go ahead and see what happens at pi over 2, just to be safe. We get 2 cosine, and that's going to now be 3 pi over 2. Cosine of 3 pi over 2 is equal to 0. So this is just going to take us back to the origin. Now let's move into our next quadrant, right? We plugged in all the values we could of the first quadrant. Let's move into the second one. So this is going to be 3 pi. No, it's not. It's going to be 2 pi over 3. This one's going to be 3 pi over 4, and then 5 pi over 6. So let's go ahead and plug and chug. Let's start off with 2 pi over 3. This one's nice to plug in. We get 2 cosine of 3 times 2 pi over 3 is just cosine of 2 pi. Cosine of 2 pi is just equal to 2 times 1, which is equal to 2. So that is going to be our last petal. It's going to be the longest length we can get to. So we got out a value of 2. Let's just plug in 3 pi over 4 just to be safe. 3 pi over 4. We get 2 cosine of 3 times 3 pi over 4. So let's do some simplification. 2 cosine of 9 pi over 4. That is going to be 2 pi plus pi over 4. So we're going to evaluate it really at pi over 4, which we know to be the square root of 2 over 2. Those 2's cancel. That just leaves us with the square root of 2, which we know is equal to 1.4. So at 3 pi over 4, we're going to go at a distance of 1.4. If we plugged in this value right here, we would also get 1.4, right? And here we have our final petal. I don't know if any of you guys noticed, but at pi over 3, we go out the radius of -2. And I went out in the wrong opposite direction. So if any of you were confused, that's why. 5 pi over 4, okay, that one still was a negative radius. Now the opposite of pi over 3, there we go. That's going to look a bit better. And sometimes you get to the end of your drawing and you realize it looks a little wonky and you can check it out, right? So I was just trying to keep you on your toes. I'm just kidding. I messed up. Sorry. So here, notice what we have. We have cosine of 3 theta and we have 3 petals. But when we had sine of 2 theta, we had 4 petals. Let's go ahead and talk about that. In general, we have r is equal to a sine of b theta or r is equal to a cosine of b theta. When b is an even number, so like 2 times theta, we have double the amount of petals. So when we had 2 theta, we had 4 petals. Now when b is odd, that just means we have that same amount of petals. When we had 3 theta, we only end up with 3 petals. Now the last thing is that a tells us how long those petals are. So here we had 2 cosine. So our petals extended a length of 2. In our first example, we had 3 sine. So our petals extended a length of 3. Now, if you want to see some general shapes, you can always use Desmos. Desmos is wonderful. So you can search up polar roses on Desmos and it comes up with this thing. So first, what we have pictured is a cosine of n theta. So you can manipulate the a value, right? And that is going to extend the length of the roses. So here I'm going to go ahead and stay at 5. So we're going to have a length of 5. So here, our n value, that's going to be like our b, what we're multiplying by theta. So here we have n is equal to 3. So we have 3 petals. Now notice if I change that to 2, now we end up with 4 petals, right? Now let's go ahead and see the sign of that. Now the sign is going to be in red. I'm going to take away the cosine real quick. Now we're looking at sine. So again, the a value is just going to manipulate the length. That's not too interesting. But the n value, right, we have n is equal to 2. We end up with 4 petals. I can increase that to 3, and now we have 3 petals. So here you can just play with it. It's really helpful. Here's n is equal to 4, right? This is going to be when we have 8 petals. Here you can see both of them. Here is sine and cosine both on there. So notice here the cosine typically is going to extend on the axes. So notice how the petals are very often on an axis, right? It's going to be an x-axis or even a y-axis. So yeah. And notice that sine of theta is sometimes on an axis. So here I'll go until we see one right there. Here we extend on the positive y-axis. Here I just had one. We extend on the negative y-axis. But very often it's just not going to be on an axis. We're going to be on the diagonals of it, right? So here we're on all the diagonals versus the cosine of this exact same thing. The cosine is going to be on an axis very often, right? So here we're on an axis. We can see all these cases how we're on an axis, right? I love Desmos. Use it whenever you can, but that is all I have for us today in this video. If you enjoyed it, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.